In this video, we'll calculate the volume of a region in 3 dimensions that's outlined here in blue. The equations for the region are given by this parabola y equal to x squared. Notice there's no z coordinate in the equation, so we should imagine that parabola y equal to x squared in the plane being extended vertically parallel to the z-axis in both directions infinitely. This forms what's called a parabolic cylinder. On the bottom, we're going to slice that cylinder at z equal to 0, and at the top, we're going to slice it at z equal to 1 minus y. Both of those are planes. Z equal to 0 is the xy plane, and z equal to 1 minus y is a plane sloping downwards in the y direction. So here's that upper boundary of the region that we're going to calculate. And we're going to find the volume of the blue region that is cut out by those two planes along that parabolic cylinder. One way to do that is to calculate it as a double integral. So what we'll need to do to find the volume is to integrate over the appropriate region R and take the surface that we want to find the area under, in this case 1 minus y, because that's the upper plane, and we're going to integrate that as a double integral now. The region R we get by projecting the points in our region down into the xy plane and integrating over that. So in 2 dimensions, here's the xy axis. It's going to be something I'm guessing is looking parabolic here, and in fact that bottom curve is indeed y equal to x squared. And then it gets cut here at this upper boundary that is a line here, and in 3 dimensions that's this line here. We can find the equation of that line, and we'll need to know the equation of that line, and we can do so algebraically. The projection occurs when z is equal to 0. So let's take the plane z equal to 1 minus y and set z equal to 0 to determine what the equation is for that line. And we'll have 1 minus y is equal to 0, and that tells me y is equal to 1. So our red line here, the upper boundary, is just y equal to 1. We can now set up the limits of integration. And I've chosen to do y first and then x, so I'm going to determine the outer ones first, dx. They must be constants, and if I look at my region, I range from x equal to minus 1 to x equal to 1. I'm now going to fix a typical value of x that's going to slice the region vertically, and I'm going to look at where it enters the region and exits the region. And in this case, it enters at y equal to x squared, and exits at y equal to 1 at the top, so x squared to 1. And you can calculate that double integral to calculate the volume of the blue region. An alternative way to do it would be to do it as a triple integral. In this case, the volume would be a triple integral over the region D, and the region D will be the blue wedge that we're trying to find the volume of itself, and we'll integrate the function 1. To do that, we begin as we began above. I'm going to write down a triple integral, and I've chosen the order dz, dy, and dx, so I should determine the x and y limits of integration first. And to do that, we just project all the points in our surface down onto the xy plane, as we've done over here in this picture, and then find the limits of integration for that region, and that's exactly what we did when we calculated the double integral. So my limits of integration for x will still be minus 1 to 1. My limits of integration for y will still be x squared and 1. And all we need to do now is find the limits of integration for z. To do that, I'm going to now fix a value of x and y. So we're going to fix a typical point xy in our region R. And in this 2-dimensional picture, I've chosen this point here for x and y. And that corresponds to some point in the projection down here, x, y, and whose z coordinate is 0. I'm then going to extend a vertical line parallel to the z-axis through my region and through my point that I've chosen. And I'm going to examine where it enters the region and where it exits the region. It enters at z equal to 0 at the bottom plane and exits at the top where z is equal to 1 minus y. And so my region of integration, my limits of integration for z will be between 0 and 1 minus y, and we've now set up our integral, our triple integral for the volume. And you should take a moment here to think about what would happen when you start calculating. The very first inner integral will result in the expression exactly that you have above. So these are really the same calculation and will give you the same answer as they should. In the following videos, we'll examine how to calculate this as a triple integral in different orders of integration.